smacking Microsoft in the face.
Microsoft almost lost.
Oh yeah.
Yeah.
Then they changed their DMR.
Yeah.
And they changed the CEO too.
Yeah.
Yeah.
Yeah, with that commercial, I think Saturday Night Live, should do an extension to the Cadillac one. The guy, drove drove 5 seconds, and then the car would stop, and he said, "Oh, that was not the charge cable; it was the garden hose." That would be funny. That would be like super funny. Who left this garden hose in the driveway? All right, so let's go ahead and trace this program, and we'll figure out what it does. It's gonna be. I mean, what do you guys think? Did you find this homework assignment okay? Kind of hard? Kind of easy?
Relatively easy.
Okay.
Start straightforward.
I screwed up and I solved it like a conditional statement.
Conditional statement? What do you mean by conditional statement? There's no conditional statement. Good one. Good try. Okay, so what we'll do is we'll trace it. On line 1, I gets initialized to bar A bar minus 1. Bar A bar is the number of elements in A, and in this case is 3. 3 minus 1 is 2. So I starts with the value of 2. Then we move on to line 2. On line 2, we're just comparing I is greater than 0, and 2 is greater than 0 is true. Okay, so we continue execution onto line 3. So line 3 really is the only line that matters, okay? Because everything else, I think we should really have those down by now. On line 3 is an assignment statement. We evaluate the right-hand side first. On the right-hand side, we have A open bracket, I minus 1 close bracket. So with something like this, we have to evaluate the expression inside the square bracket first. I is 2, 2 minus 1 is 1. Okay, so we have 1. So we have 1 inside the square bracket, which means A square bracket I minus 1 is referring to A bracket 1. A bracket 1, according to column E, has a value of 2. So the entire right-hand side becomes just the value of 2. So now the question is, what are we doing with the value of 2? We store it to the left-hand side. The left-hand side is A bracket I. I has a value of 2 at this point. So we are basically storing a value of 2 to A bracket 2, which is column F. So that's why column F, which currently has a value of 4, is going to be overwritten by a value of 2. And then we move on to line 4. Line 4 is subtracting 1 from I. I goes from 2 to 1. And then we continue execution back onto line 2, which is the beginning of the loop. I is 1. 1 is greater than 0 is true. We go to line 3 again. When we get to line 3 this time, I has a value of 1. So on the right-hand side, I minus 1 is 1 minus 1, which is 0. So it becomes A bracket 0. A bracket 0, which is column D, has a value of 5. So the entire right-hand side of line 3 becomes 5. The left-hand side is A bracket I. I has a value of 1. So A bracket I refers to A bracket 1. A bracket 1 refers to column E. So column E is the one that is updated with a value of 5. And then we go to column 4, we go to line 4. Line 4 is subtracting 1 from I. I goes from 1 down to 0. We go back to line 2. 0 is greater than 0 is false. And then we are done. Get to post. That's all this program is going to do. In other words, it's basically shifting values of the array elements, by 1. In this case, in this class, to the right-hand side. In my morning class, it's going to the left-hand side. All right. Are there any questions about this trace? Are there any questions about how each line is performing what it's supposed to? Yep.
For line number 3, when it's A bracket I minus 1, why doesn't it do A bracket I, which is 2 minus 1, so it'll be A bracket 1?
Because I minus 1, the entire thing is inside the square bracket. So you have to evaluate the expression I minus 1 first before you perform the indexing. Okay, all right. Any other questions?
Make sure of that on Tuesday, because I was confused by that also.
Right, right. Yep, That's probably is one of the most asked questions with constructs like that. Is when do we do the -1? Do we do the indexing first, or do we do the -1 first? Now because I minus 1 as an expression is inside the square bracket, so you have to evaluate that expression first before you can perform what the square bracket is supposed to do, which is indexing. All right. So if this is okay, we're going to move on to the new homework assignment. I'm just going to give you a look of the new homework assignment, and then we'll trace binary search, in this class. So we'll move on to the next topic. In topic 6, we have array 2 as your new homework assignment. So here's topic 6. We talk about binary search in class, and here's a homework assignment involving binary search.
Next Thursday.
It's due in a week. Yep, it's due on Thursday next week. All right, so this is binary search.
Bad. No, it says bad.
Yep, it's bad binary search because it is incorrect.
Well, it's unfortunate.
That's why it's bad. Okay, so this is an incorrect version of binary search, and your job is to trace it. Okay, and tell me whether there's a problem with it or not, and if so, what is the problem? Okay. So your job is not to fix it, but to tell me what this particular program is going to do in 3 test cases. So we have sheet 2, 3, and 4 as test cases. Now in this is the most important part. If you think the trace will not end because it is an infinite loop, you have to tell me why it is an infinite loop. So typically what you need to do is to go through 2 iterations with no changes to the values of the variables. Then for sure it is an infinite loop, because the 3rd iteration would be the same thing. Okay, is that making any sense? So if you go through 2 iterations and no values has changed at all, then you know for sure it's going to be an infinite loop. All right, so I'm going to leave this one here, and then what we'll do today first is to take a look at binary search, the correct version.
I have a question about the
Yep.
assignment. When we do those 2 iterations and we realize that it will go on infinitely, where do you want us to provide the explanation?
You can just use one cell, in your trace to indicate that, for that particular test case, it's going to be an infinite loop. So it may not be an infinite loop for all test cases. Okay, with some of those, it may actually get out.
Okay.
So you have to kind of test which one is incorrect and comment only on that one.
Okay.
Yep. All right. So what we'll do next is we'll go ahead and take a look at the correct version of binary search, and then we'll trace at least one of the test cases through this one. Okay, so binary search, we talked about this on on Tuesday. So what we'll do is we'll present the algorithm itself.
So we're not gonna finish trying to find out what it is on the notepad or whatever.
Find out what it is.
Because we. Yeah,
Oh, we were
Tuesday.
doing revisions to the.
Oh, okay.
Yeah.
I forgot about that.
I did.
Very good. So one thing we can do is to take a look at what we did on Tuesday.
We need to try to figure out what happens to B and what happens to E.
What?
The placeholders, what happens to them, like B gets question mark, and else.
Oh, okay,
E
I
gets-
see. Okay, so we'll go ahead and finish that first. Today is the 3rd, so we're looking at the 1st. And this is
roll sheet.
I forgot the roll sheet today, so you guys
Well, it's there.
It's not going to help anyone who's currently in class, right? I mean, only people who are currently not here. So they'll be watching the video and go, woohoo, free ride, free pass. Okay, so let's see. Let me a little bit further.
90-minute rule.
Okay, so this is where we have left off. I'm going to change the resolution so that we can zoom in. Okay, so this is where we left off last time. So what I'll do is I'm just going to continue with this revision and then finish this one first, and then we'll talk about how to trace the algorithm. All right, so we'll go ahead and let's still use mousepad for this purpose. Okay. So this is revision 6 from last time. Loop we already know, kind of how to get to the index m, which is the index for the element to compare to. And we say we'll compare A bracket m with k. If they are the same, then there's nothing to do. We just say, woohoo, done. Eureka. Okay. Which means, Eureka means, found it. I found it. And also a name of a city in California, one of the northmost cities. Okay, B gets some value here. E gets something here. And if and loop exit when A bracket m equals k, or okay, let's see. Or the portion of the array that may contain k is empty. Okay. Portion. Wow, I can actually touch type. Most of the time I will have some typo. My accuracy is not really that good. All right, so this is revision 6. And what we were about to do is to figure out what those question marks are supposed to be. Okay, so let's go ahead and do this with revision 7 because that's from last time. So now we can start with revision 7 and try to figure out what to do with those question marks. All right. So with this particular with these two question marks, I'm asking, what if A bracket m, an element in the array that I'm comparing to, is actually less than the value that I'm searching for. Okay. Now, because the array is assumed to be sorted in an increasing order, that means A bracket m minus 1 is also going to be less than k. A bracket m minus 2 is also going to be less than k. In fact, everything before A bracket m would also be less than k. But anything that's less than k cannot possibly be equal to k. So now I can rule out that portion. So that's why we are moving b, which is the index of the first element of the entire of a range in the array that may contain the value k. So we're moving b forward. The question is, how far forward should we move it? We have a few options. We can move it to m, but that's not really a good idea because we just proved by the comparison that A bracket m does not equal to k anyway. So what is the first element or the index of the first element that may equal to k? Plus 1, exactly. Okay, and using the same type of argument, if A bracket m is greater than k, it also means A bracket m plus 1 is greater than k. A bracket m plus 2 is greater than k. So anything after A bracket m cannot possibly be k. So we know that we have to move the n backwards. So in this case, we move the n back to m, but A bracket m is proven not to be the same as k anyway, so we have to move it, one element before, which is m minus 1. Okay. Are there any questions about how I filled in the question marks for binary search? Questions? Okay. All right. And because we know that m is used, or m plus 1 is used to update b, and m minus 1 is used to update e, we know that for each iteration, as long as A bracket m does not equal to k, we'll be moving one of those two. Okay, we'll be moving b forward, we'll be moving e backwards. Okay, we'll move only one at a time, but we know that we have to change them. And because they're moved to m plus 1 and m minus 1 respectively, we also know that they are going to inch, in this direction. One is going to go in this direction, the other one is going to go in this direction with each iteration. But they will have to change at least by 1 for each iteration, which means at some point they're going to meet. Okay, when they meet, which means when b equals to e, we have one element left to examine. But when they cross over, then we are done. So that's why the indication that the portion of the array that may contain k is empty is when b is greater than e. Is that making any sense? Mm-hmm. Because normally b is less than or equal to e to mean that we have some portion in the array that may still contain the value that we are searching for. But when b is greater than e, which means the beginning is past the end, it doesn't make sense anymore, and that means the range of the array that may contain the value is now empty. right. So after this, we can just go through one more iteration and then we can trace it. The last iteration, which is revisions 8, we're going to fix a few things all at once. Because B has to be initialized to something. What do you think is the index of the first element that may contain the value k before the first comparison, before any comparison? So before any comparison, the entire array may contain the value that we're searching for. So which means the index of the first element that may have that value is going to be the very first element.
A bracket
But
0.
what is the index of the very first element?
A bracket 0.
0. Just 0, not a bracket
Yeah.
0. Because B is only storing the index, not the value of that particular element. The n, or the index of the end of the entire array is,
6.
say again?
6.
Nope.
Bar A bar.
Bar A bar
Minus 1.
minus 1. Okay, it is minus 1. You have to remember the minus 1 because we're counting from 0. Yep.
How come it's not 1? How come it's 0 and not 1?
Because we count from 0.
Oh, okay, okay.
Yep, because with most, but not all programming languages, array indexing starts with 0 and not 1. It is counterintuitive because we don't count from 0 normally, but when we are dealing with arrays, it is actually making sense because 0 means it is at the beginning of the entire array. We are 0 element from the beginning of the entire array. That's basically why we're starting from 0. Okay. And we know that this is going to be a repeat until loop. The reason why I know that is because in order for me to evaluate the condition to determine whether I'm getting out of the loop or not, I need to rely on the value of m. But the value of m is actually set inside the loop itself. So that means I have to perform at least one iteration in the loop in order to evaluate the condition to determine whether I should stay in the loop or get out of the loop. And that's why it is a post-checking loop, because I have to perform at least one iteration before I can decide whether to get out or not. So that's why we have a repeat until loop, which is easy because the condition that we already have is an exit condition already, so that's fine. Okay, let's take a look at inside the loop here. Inside the loop, we have the same thing here, but instead of just saying m is b plus e divided by 2, which captures the logic of binary search, but it still needs some refinement because when you look at b plus e divided by 2, it can potentially be a fraction, or a number with a fraction. So what we need to do is to make sure that this becomes an integer. And the way we do this is to use the floor function, or one way to do it is to use the floor function. The floor function, I have already described it here. The floor function means we are taking, or we are computing the largest integer that is less than or equal to the number that we are trying to consider. So in this case, the floor of 2.3 is the largest integer that is less than or equal to 2.3, and in that case, it is 2.
So it's basically rounding?
It's
Rounding
not
down.
exactly rounding down. It is actually, it's about the same, but it's not exactly. Okay. The floor of 4 is 4 itself because 4 is the largest integer that is less than or equal to 4. So don't forget about the equal part. The trickier one is the floor of negative 1.5 because as far as negative 1.5 is concerned, the largest integer that is less than or equal to it is actually negative 2. Okay, because negative 2 is actually less than or equal to negative 1.5. Okay. But fortunately, since we cannot have negative numbers as indexes, you won't encounter tricky cases like that. Okay. Are there any questions about the floor function? No questions? And in the notes, yep.
How do you do the actual math for the very first one is it's 2 and 3.
This is 2.3.
2.3. Oh, 2.3.
A decimal.
Yeah.
Okay.
So just rounding to the left.
Correct. Rounding to
Number
the
line
left
such
is the
as
correct.
that.
Yep. You want to pick the largest number from the left-hand side that is touching or to the left of the number that you're dealing with. Yep.
So it was the top one 2.8.
It will still be 2 because the largest integer that is less than or equal to 2.8 is still 2. Now in an algorithm like this, you will never encounter 2.8 because b and e are supposed to be integers to begin with. So if you add an integer to another integer and you divide the sum by 2, the worst you can do is it's a something 0.5 as a half, basically. Okay. Are there any questions about the floor function? The floor function can also be represented as a symbol. So if you want to take the floor of x, in some math books, they use this symbol to indicate the floor of something. And of course, you already know what the ceiling looks like, right? Just flip the operator, that becomes the ceiling of x. And the ceiling is really just the opposite of the definition. It would be the smallest integer that is greater than or equal to x. So and in this case, you can use floor. You can also use ceiling. You can use round if you want to. Just any way to convert something 0.5 to either the previous integer or the next integer will work just fine. Okay, it doesn't have to be exactly the center one. So I just picked floor because that's the easier one to use. If they are the same, so in this case I cannot do a compare and then look at the result of the comparison. So I would just be ending up doing the comparison. So if a bracket m is less than k, we'll do one thing. If it is less than, we're going to update b, so the b becomes m plus 1. Else if a bracket m is greater than k, then we want to update e in the opposite way. It becomes m minus 1. And if, okay. But what about when they're equal? I'm not even checking whether they're equal or not. When they are equal, I got nothing to do, okay? Because I have just found it. I'm just going to let it up to the exit portion of the loop to decide, oh, a bracket m equals to k, it's time to exit. So as far as the conditional statement is concerned, there's really nothing to do. Okay. Are there any questions about the correct version of binary search? Yep.
What would you put in place of Eureka revision 7 for revision 8, or like what?
Oh, wait, isn't it missing the bottom part? There we go, because it wasn't showing. I could
Yeah,
see the
but it will
scroll
exit,
right there.
because the condition is not checked in the conditional statement. It is basically ignored. That is the one condition that the conditional statement is going to say, okay, I'm not going to do anything about this one. Because there really is nothing to do inside the loop, because the loop will simply exit after the conditional statement.
It's not necessarily a dead branch as much as a useless one.
Correct. It is a useless one, so I don't even specify that branch in the conditional statement.
Especially because it's one of the conditions to getting out of the loop, so it would be pointless.
Yep. But more
It's
specifically,
because it does
there's nothing to do, right? There is nothing to do for that case. All right. Now, if I want to indicate the result using a found variable, I'll just go ahead and do it like this. In other words, if a bracket m does equal to k immediately after the loop exits, that means I have just found an element in the array that matches the value that we are searching for. All right. So what we'll do now is to take revision 8, which is the correct implementation, and then what we'll do is we'll go ahead and trace it. So we'll say repeat.
E.
Sorry?
E. It's at 0.
Oh, that's right. E should be getting bar a bar minus 1, which is the index of the last element of the entire array. M gets the floor of b plus e divided by 2. If a bracket m is less than k, then k is, we move b forward in this case, so b gets m plus 1. Else if a bracket m is greater than k, then we have to move the n to m minus 1, and if until a bracket m equals k, or b is greater than e, found gets a bracket m equals k. That's my algorithm. Let's do the indentation thing. Okay, so for the indentation, if I use the top-down approach to do the indentation, the first thing I would do is to scan through this whole thing. Consignment statement, no need to do any type of indentation. Assignment statement. Here's a repeat. So for a repeat, I know I'm expecting an until. So in this case, I find the until all the way down here, and there are nested, there are no nested repeat until, so this makes it kind of easy. So I know everything in between, they have to be indented exactly once first. So when I look at the stuff in between the repeat and the until, we have an assignment statement, nothing to do. We have a conditional statement. So with this conditional statement, I have to identify the end of it, which is here, but it also has a second, condition to evaluate. So these 3 lines I do not indent. It is all the other lines that I'll be indenting. So those will be the 2 lines that I'm indenting, and that's it. So now the program is indented, and we are ready to trace it. All right. So for examples, of what to do, when we are tracing this, I'm going to use the same test case or one of the same test cases as your homework assignment, which is good and bad at the same time, because some people can look at this as good because now we are using the same test case, but it can also be bad because it can be confusing as well. So it all depends on how you look at it and whether you feel comfortable being able to differentiate between the correct version of binary search and also the not so correct version of binary search. All right, so we'll go ahead and make this a little bit smaller because I need more space for the trace, because there is an array to display, so it takes up a little bit more space than most of the other traces. Found is not even here yet, but I can deal with found later, okay, because it's the last thing that we are going to do. All right, so what we'll do is we'll start with this trace. The precondition is this part here. In other words, I'm looking for a value of 3, that's what k is, in an array that does not contain a value of 3. So we want to take a look at how this algorithm is going to exit, and just in general, how do we trace something like this? On line 1, b gets initialized to 0. On line 2, e gets initialized to bar a bar, which is 4. 4 minus 1 is 3. On line 3, we don't trace anything, so we skip all the way to line 4. Do not trace line 3, okay? Because I have explicitly said it, do not trace line 3. Anyone who traces line 3 will have points deducted.
I guess 10 takes the place of that.
Okay, so now we're getting down to line 4. Line 4 it has to compute b plus e first. B plus e is 3. 3 divided by 2 is 1.5. The floor of 1.5 is 1, so that's why m is going to end up with a value of 1. On line 5, we evaluate the condition a bracket m is less than k. A bracket m is a bracket 1 because m has a value of 1. That has a value of 6. We are looking for 3, and so 6 is less than 3 is false. Okay. So we move on to which line? 7. We move on to line 7. That is correct, because if the first condition does not match, then we have a second condition in this case because we have a multi-branch conditional statement. On line 7, we are still comparing the same elements, but we are basically reversing the direction of the comparison. A bracket m has a value of 6, and then k has a value of 3. 6 is greater than 3 is true. Okay. So we go to which line at this point? Okay. We go to line 8. And what do we do on line 8? M is 1, m minus 1 is 0. So we update e with 0. No, that cannot be right. I messed up somewhere. I think I messed up the conditions. Okay, if k is greater than m, a bracket m, oh, that's right.
I think line 4 has to be 2.
On line 4? No, line 4 is updating m correctly. A bracket m is a bracket 1. 6 is less than k. K is 3.
Yeah, I think line 4 is because 3 divided by 2 is
1.5. The floor of 1.5 is 1.
Oh.
So that part is correct. I think I have reversed the conditions. Sorry?
I think so too, yeah.
Yeah, I think I reverse the conditions or reverse the way I update B and E. Okay, if A, okay, let's figure this out. Okay, if A bracket M is less than K, then A bracket M minus 1 is also going to be less than K. So in that case, I want to update B, which is correct. That makes sense to me.
It's correct.
Yeah. So we're going to update E with M minus 1.
Yeah, that's exactly what the statement reads.
Okay, I think that's probably correct. Okay, let's go ahead and update E with M minus 1, which is 0. Okay, that's actually right. It just looks wrong to me.
Just doesn't feel right.
Doesn't feel right, but it's actually right. Okay, so let's see whether it works out correctly or not. Okay. We get on to line 10. On line 10, we have to evaluate to the disjunction. The first part is A bracket M equals K, which is going to be false because we just checked A bracket M versus K, and it is a greater than relationship. So this part is false. This is a disjunction. Can I make a conclusion right now and say the entire disjunction is either true or false?
No.
Nope, because just because the left-hand side is false doesn't mean I know anything about the entire result, because the right-hand side now determines the entire result. So I have to evaluate the right-hand side first, but right-hand side also. So B is 0, E is also 0. 0 is greater than 0 is false. So we have false or false, which means the entire thing is false. Now this is the exit condition. If the exit condition is false, we are not getting out of the loop. We are going to go back to the beginning and do the whole thing again. So from line 10, we go back to line 4. And this time it's easy to compute M, because M is 0 plus 0, which is 0. 0 divided by 2 is 0. The floor of 0 is also
So
0. Okay, so the whole thing becomes 0. Then we go on to line 5. On line 5, we compare A bracket M to K, looking for a less than relationship here. A bracket 0 has a value of 2, K has a value of 3. 2 is less than 3 is true. It's true. A bracket 0 has a value of 2, K has a value of 3, 2 is less than 3 is true. So we go to line 6 in this case. Line 6 is going to update B, so it becomes M plus 1. M has a value of 0 at this point. 0 plus 1 is 1, so B becomes 1. After line 6, where do we go?
Line 10.
Line 10, that's right, because it's a multi-branch conditional statement. We take one branch, we get out of the entire conditional statement. On line 10, we compare A bracket M with K first. We already know that A bracket M is less than K in this case, so that means equal to is false. Then we have no choice but to evaluate the second part of the disjunction. B is greater than E is true, false or true is true. So on line 10, we have a true condition, which means the exit condition is met. In this case, we get out of the loop, we end up on line 11. On line 11, we have to evaluate A bracket M equals K. A bracket M is A bracket 0, which has a value of 2. K has a value of 3, 2 equals 3 is false. So the found variable is going to end up with a value of false. And then we get to post, and we are done.
Do we have to write, let's see, A bracket M and bracket
No,
equals
you don't have to, because we are not determining which way to go. So you just have to evaluate it and put it inside the variable. If you want to write down, what the condition or the result of the condition, that's fine too. Yep.
So that's very similar to the homework that you said. So how is it going to be difficult finding the mistake in the new homework? I mean, how?
It's not going to behave the same way. The homework assignment is not going to behave the same way. This is the correct version, which means if you look at the algorithm, if you have this condition or this condition, which means A bracket M does not equal to K, then we'll either be moving B forward, increasing the value of B, or we'll be decreasing the value of E. So whether it's going by half or not doesn't even matter, because we know they have to be getting closer and closer together. And at some point they're going to cross over. So if you cannot find the element, you will still be exiting, because B and E will cross over, and that's an indication that we have nothing left in the array that can still have the value K. But when you look at the homework assignment, it's wrong at multiple places. The first part, or the most obvious part, is B gets M or E gets M without the +1 or the -1. That means, eventually they can stay at the same place. If you have only one element left and it is not the value that you're searching for, that means B and E will be the same, and so M, B, and E, all three will be the same. But without the +1 or the -1, they will stay the same the whole time. They cannot change anymore.
So it's just infinite.
So that's why you can end up in an infinite loop. Yep. All right. So are there any questions about binary search, the correct version of the algorithm? No questions?
So we just explained the fact that it is an infinite loop, and we just
Say
kind of
why.
give our explanation.
You do have to trace it first, so I don't want to see anyone, just in the trace. The first line is this is going to be an infinite loop. No need to trace it.
I can
Because
tell.
someone's going to try it unless I say no, do not do that.
Even then, some people still
Yes,
don't.
even I say that, somebody's going to try that.
So you wanted 2 or 3 full loops before?
Only 2 iterations of the same values,
Yeah.
because that's the only time you can tell, okay, it's not going to change anymore. Sorry?
That's on homework.
Yep. All right. So once we're done with binary search, we're going to move on to subroutines. Okay, so this is actually starting a new topic that is, well, I wouldn't say it's not related to whatever we have talked about before, but it's an extension. It's a handy way to do certain things. So let me get back to the beginning part of the entire page and kind of point out where we are now. We are now in topic 7. Now that we're in topic 7, I also kind of have to point out, how to read these notes. The first portion, they're all useful, so you can still read it in order, but the last link is the one that is kind of cleaned up. Okay, so you might want to start, just reading the last link first, because it is the more cleaned up version. It's more concise. I like it better, but some people may want to kind of go through all of the other notes as well. They're not conflicting, it's just different ways of presenting the same concept. Okay. All right, so the first thing what we'll do is we'll go ahead and take a look at a particular program with subroutines, and then we'll basically say, okay, how does it work? What does it do? So we'll use this. I will just use the same spreadsheet here. I'll define a subroutine. We'll just call the subroutine XYZ in this case, because I don't want to kind of keep track of what it's supposed to do. We'll just say that it's supposed to double the value of x, and then it will just add 1 to the value after doubling, and define sub. When we define the subroutine, it is the same thing as a dictionary definition of a word, which basically means if I refer to XYZ, this is what XYZ means. Okay, it means double the value of x and then add 1 to it. That's basically what it's supposed to do. Outside of the subroutine, we can actually start to do something about the variable. So in this case, let's say x starts with a value of 5. Okay, and then we can say, you know what? At this point of the program, don't ask me why, but at this point of the program, I want to double the value and then add 1 to x.
Why not?
Yeah, why not? So instead of just saying x gets twice of x and then add 1 to it, now I can say, oh, just go ahead and invoke xyz. Okay. In most programming languages, they do not use the word invoke. They use the word call. But basically, it's just activating xyz. Okay. Do whatever xyz is defining. Okay. After this, I might have some other things to do about x. So I might want to say x gets x times 8. Okay. And then after that, I want to double the value and then plus 1 again. Okay, but I don't have to spell out doubling and then plus 1, because I know that subroutine XYZ is going to do that. Yep.
Do you define that at the beginning, or is that just part of the program?
Or maybe you can define it halfway through the program.
That part depends on the programming language. With most scripting languages like Perl and PHP, you can define subroutines anywhere you want to. But with C and C++, everything has to be inside a subroutine, including the code that you execute to begin with. So we'll talk about that later. But for the time being, we'll just say that you can define subroutines anywhere you want to. But as a convention, we typically put all those at the beginning of a program. Did I start the recorder? I think you reminded me to start the recorder.
I believe you do.
Yeah.
Okay.
Wouldn't hurt to check.
I'm just a little paranoid about that. Okay. Okay.
It
All right.
Is the volume on?
Hmm?
Is the volume on?
I think
we've
so.
been recording once.
Make sure
Not
we are
this
not
year.
recording a silent movie. No. Yes. Gotcha. All right, so we'll give these line numbers, and then we'll use another window for the trace. Now, when I trace this, don't copy everything, okay? Or at least, don't copy everything until I tell you to copy it, because I will need to leave some spaces, okay? We'll leave some empty lines to backfill later on. Okay. Now, the whole purpose of a subroutine is kind of like, we use those, we use this concept all day long, okay? For instance, how do you wash a single dish?
Put it in the dishwasher.
Very good
Okay,
summary.
your dishwasher is broken. How do you wash it? How do you wash your dishes?
You buy a new
I
one.
never wash my dishes. I only use paper plates. I actually know someone who does that. And I'm not talking about. I'm not talking about only when they have to entertain 20 people or more. It's like, okay, I don't want to do dishes. I don't even have 20 dishes. No, they do this on a daily basis, and there are only 2 of them. Okay, and on a daily basis, they would use paper plates, just for eating, and at the end of each meal, they just have to toss everything into the trash can.
Save it till it takes water to make them too.
Okay, but getting back to washing dishes. Okay, so let's just say that we wash dishes using this procedure. Okay, put the dish under the under water. Rinse off all the stuff. Use a sponge. Use soap. Actually clean it. Rinse it, and then put it onto the drying rack.
Subroutine.
Hmm?
Subroutine.
Subroutine. Okay. So if that's the procedure of washing a single dish, and I want to tell my one of my kids and say, okay, when you're done with the soup, I want you to wash that bowl, and then I want you to clean up the table, and then I want you to wash the pot. Okay, that you use to cook the soup. Yeah, that's why I like programming so much, because it gives me that sense of reliability. I know the program is going
As long
to
as I
do
tell them
whatever
to do
I
it
say.
correctly.
Yep. So if I say that, they know what to do. I don't have to spell out the details of how to wash one thing, over and over again. I only have to define it once. This is how you wash a dish, and then I can just say wash the bowl or wash the pot. Okay. And that's the same thing, okay? Defining a subroutine like XYZ simply means that I can just say, hey, do XYZ, and then every time I say that, it means whatever is defined inside or between define sub XYZ and end define sub. Now this time there are only 2 lines, but I can have 20 lines, 30 lines in between. I don't have to spell out those details over and over again. So that's one reason why we use subroutines. All right, so getting back to the trace part here, there's no need to use comments because I don't have any conditional statements for loops to deal with. So I can start with line number. I have one single variable x to deal with, so it uses up another column. The precondition is I don't need to know anything about x because I'm going to overwrite it to begin with. Okay, so that part is fairly easy. The next question is, where am I going to start with this program? I don't start with the definition of a subroutine. There's nothing to do about the definition of a subroutine. In other words, it's just like an entry inside a dictionary. Okay, how many people would read a dictionary as if it is? I just feel like reading a dictionary. I know people who used to do that. I used to know people who do that. But most people would not do that. Okay, you don't look up a dictionary unless you have to, right? It's the same thing here, okay? You don't really need to know what a subroutine is defining until someone asks you to do something that relies on the definition of a subroutine. So that means I don't start execution from line 1 to line 4 because it's just defining something that I might need to know later on. Okay, so we start execution on the first line that is outside of the definition of a subroutine, which in this case is line 5. Okay, we start with line 5. X gets initialized to a value of 5 on that line, and then on line 6, what do you think line 6 should do? line 6 means we want to continue execution at whatever code that has a name of XYZ, and then we look it up and go like, oh, okay, I guess we found subroutine XYZ to be from line 1 to line 4. So line 6 doesn't seem to have anything to do except to continue execution in the named subroutine XYZ. Okay, but I'm going to leave one row empty here because we'll backfill that later on. So we'll continue execution inside the subroutine. Line 1 doesn't do anything useful, so we'll continue execution on line 2. Line 2 is doubling the value of x. X goes from 5 to 10. Line 3 is sequential to line 2. It's just adding 1 to x. X becomes 11. And then at this point, now I have a question. I'm now at the end of a subroutine. In other words, I have just put my clean bowl onto the cleaning rack. But my instruction was to clean the bowl, to wash the bowl, and then clean the table. So now I have to remember, what am I supposed to do after washing that bowl? Oh, to clean the table. So in this case, where am I supposed to go after the last line that is useful inside the subroutine? Line 7. Okay, line 7 makes perfect sense because I got here inside subroutine XYZ because of line 6. So when the subroutine is all done, we should continue execution on line 7. Leave one row empty here because we'll backfill it with something. Okay. On line 7, we are just multiplying the value of x by 8 and then storing it back into x. So x becomes 88 as a result. After line 7, we go to line 8, which doesn't seem to have anything to do except to continue execution in the subroutine again. And inside the subroutine on line 2, we are doubling the value of x. So it becomes 176. And then on line 3, we add 1 to x. It becomes 177. And then after line 3, we have to remember where to go back to. Where do you think we should go back to? There's nothing after line 8. Post. All right. Sounds good. All right. Is this okay? Because is everybody kind of expecting this would be the flow of the program? When I invoke a subroutine, when the subroutine is done, I go back to where I was doing before and continue with that. Okay. So the question now is, how did I know that? Okay. Let's look at all the important transitions. From line 5 to line 6, that's a no-brainer because they are sequential. Okay, line 5 and line 6 are sequential. After I'm done with line 5, I get to line 6. Even from line 6 to line 2 is also kind of simple because I can link those two lines by the name of the subroutine. Line 6 says, go do XYZ. Oh, what is XYZ supposed to do? Oh, here's the definition. Okay, so that part is not mysterious. Line 2 to line 3, not difficult. They are sequential. The difficult one is from line 3 back to line 7. How would I know that at the end of the execution of this subroutine that I'm supposed to go back to line 7? Now, you know because you were tracking this mentally. Okay, because you were tracking this mentally and say that we got to line 2 and line 3 because of line 6. So when line 2 and line 3 are done, we should go back to line 7. That's basically what went through your mind. You were tracking this mentally. The same thing happens when you went from line 3 to post. It is also your mind tracking and say that we got to line 2 and 3 to begin with from line 8. So when we are done, we're supposed to go back to whatever is after line 8, but since there's nothing after line 8, we can make a conclusion and say that we're all done at this point. Is that okay so far? Okay. All right. So what I'll do next is to explain the mechanism by which a computer can keep track of all these things. Because unlike you, a computer does not have, quote unquote, a mind to say that, oh, I'm going to reason this out and say, okay, I'm supposed to continue execution here because if I look back at the trace, I started from here. Okay, a computer needs very explicit instructions and information in order to perform those operations. Yep.
Is it like having a view state in C#?
Is it like having a
view state? Like, you know how like when a code gets pulled up, it's just for an instant, but like if you press it again, it restarts and goes back to the instance. But if you put in a view state, then it saves where you were at, and then it goes back to where you were.
Oh, it's not quite like that. I guess it is related in a way, but it's not exactly like that. This is very common in most programming languages, with a call, invoke and a return, how to get back from a subroutine, basically. So the way it does this is line 6 actually is important. It has got two things to do. The first thing line 6 is going to do, or any invoke statement is going to do, is to allocate the leftmost available column. Okay, at this point, column A, column B are both used. What is the leftmost available column?
C.
Column C. So the first thing it's going to do is to allocate the leftmost available column and label it return line number. Return line number. And then in that column, it will basically say, okay, I'm on line 6 right now. I'm about to go to the subroutine, but I'm going to remember when the subroutine is done, where is it supposed to go back to? Where do you think we're supposed to go back to in this case? Which line am I supposed to go back to after the subroutine is done?
7.
Line 7, okay? So we write down 7 here. All right? That's the first thing that a invoke statement is supposed to do, is to remember where the subroutine is supposed to go back to when it's done. And then the second thing it's supposed to do is to continue execution in the subroutine, which means in this case, continuing execution on line 2. Okay, that part we know already. That part is the obvious part. Now, when we are done with line 3, what are we supposed to do? Line 4 is end define sub. It sounds like the same kind of thing as end if, end while, or repeat, or else, which is basically a marker in the program that marks the end of something. It doesn't seem to have anything to do, but in this case, it actually does. Okay, so that's why in the subroutine, we also have to trace the line that is labeled end define sub. In this case, it's line 4. Line 4 has got two things to do. The first thing it does is to look up the rightmost active return line number. Okay, what is the rightmost active return line number in this case? Which column?
C.
Column C. Column C is telling us to continue execution on line 7. So at this time, if I were to trace this program sequentially, at this time I will make a note and say that, oh, the return line number column is asking me to continue execution on line 7, and then I'll write 7 here as a result to make a note that we're supposed to continue execution on line 7. That's the first thing it's supposed to do. The second thing it will have to do is to say, okay, I don't need this column to remember the return line number anymore, so as a result, I'm going to mark this line as, let's see, would that work? Yep, it will work. Okay, so I'm going to mark this with a cross out or strike through to basically say that this column is now deallocated as of row 8. Okay, as of row 8, column C is now once again available. The strikeout basically means it is now deallocated, it is not used anymore. Are we doing okay so far with that notation? So this is the first time we see a program that will dynamically allocate a column, make use of it, and then free the column or deallocate it. Okay? And we will continue to see more stuff along this line. Okay, so we continue execution on line 7. Line 7 does what it's supposed to do, continue on to line 8. So line 8, which is an invoke statement, will do exactly what we did before with an invoke statement, allocate the leftmost available column. Now, because column C is now deallocated, it becomes my leftmost available column. So we are not going to allocate column D. We will continue to reuse column C at this point. So column C is now our return line number column, and post is what we need to do here because we don't really have a line after line 8, which basically means when subroutine XYZ is done this time, we will just basically make a conclusion and say that we're all done. There's nothing else to do. And then the second thing line 8 is going to do is to continue execution in the subroutine that we have named, in this case starting on line 2. Line 2, line 3, not a problem. But when after line 3, we have to go to line 4. Line 4 has exactly the same two things that it has to do like before. It has to look up the rightmost return line number. Once again, that will be our column C in this case. It tells us to continue execution at post. I make a note here, and then I have no use of that column anymore. So on line 4, or row 14 of the trace, I will deallocate that column one more time so that that concludes the trace. Yep.
Do we actually have to cross it out every time?
Yes. Yeah, we have to indicate whether we're allocating or deallocating. The strike through is there to indicate that we are deallocating.
So like if there was a line 9 and 10.
If there was a line 9, then row 11 would have 9 in it, because that would be the line to go back to after XYZ is done.
It would kind of be like repeat sequence.
Right. All right. Yep. Go ahead.
So line 4, the undefined sub, that's just canceling out the reminder. That's just.
It's making use of the reminder that I set up earlier, and then once I make use of that reminder, I want to free up the resource because I don't need that reminder anymore. All right. Is that okay? All right. So let's take a look at a second example. The second example is going to be kind of like this one, except it's slightly more complicated. It's more complicated in the way that we can invoke inside the subroutine. Okay. Yep. Go ahead.
I have a question about that. I was reading the notes and it says that you can invoke the same subroutine inside itself.
Yes.
But wouldn't that just loop on forever?
Not necessarily, because the invoke statement can be inside a conditional statement.
Oh, okay.
So then you can stop at some point, but once you stop, it will start to unwind itself.
That makes sense.
Yep. So we will definitely get there, but before we get there, we have to talk about non-recursive subroutines first. So in this case, we have a non-recursive routine ABC, and its job is to double the value of x. But guess what? It also has something else to do. It's going to invoke another subroutine. Let's just call it DEF. And now we'll define DEF, and DEF is just going to add 1 to x, like that. And just like the previous example, we'll initialize x with a value of 5. We'll invoke ABC, and then we'll invoke DEF. Okay, so we'll try to figure out what we will do in this case. I'll fix the indentation shortly. So here's indentation, and there we go. In the trace one, we have to also add a new sheet. There we go. All right. Same thing as before, we have one column for line number, one column for variable x, at least initially. Except for the line number column and also the comments column. Every column that we're dealing with from this point on, they represent locations in memory. So the more columns you're using, the more memory you're actually using as well. All right, the precondition of x is, we don't need to know anything about it. This time, where should we start? What is the first line that is outside of the definition of a subroutine?
8.
Line 8, okay, so we start with line 8 here. X gets initialized to 5, just like before, and then we move on to line 9. When we move on to line 9, we'll do what a subroutine invocation is supposed to do. 2 things. One is to allocate the leftmost available column, in this case it's column C, label it return line number, and then write down the next line after the invoke statement. So logically speaking, where are we supposed to go after the invoke statement on line 9? Well, go to line 10. Okay, that sounds easy. And then the second thing a invoke statement is supposed to do is to go to the subroutine or continue execution in the subroutine that the invoke is naming. In this case, it's naming ABC, so we should continue execution on line 2, which is inside the subroutine that it is invoking. Are we doing okay so far with the invocation process? On line 2, it doesn't do anything that's too exciting, just doubling the value of x, so it goes from 5 to 10. And then on line 3, we are going to invoke again. Guess what? This should get boring at this time. Because to invoke a subroutine is to repeat the same 2 steps that we have done over and over again. Allocate the leftmost available column. In this case, it's column D, because column C is in use at this point. So we have to use column D for my other return line number. And this time, where am I supposed to go back to after line 3? 4. Go to line 4. That's right. line 4 does have something to do, so we have to say, okay, let's go back to line 4 and see what we have to do on line 4. But right now, I'm not too worried about line 4. Right now, I need to continue execution in the subroutine that I'm invoking, which is DEF. DEF starts on line 6, and it doesn't do anything too exciting either. It's just adding 1 to X. But after line 6, I have line 7. Line 7 is the end of a subroutine, which means it has got 2 things to do. It has to look up the rightmost active return line number column. What is my rightmost active return line number at this point? Which column? Column D, and it's telling me to continue execution on line 4. Okay, so that's how I make a note here. On line 7, the first thing to do is to look up this column and say, okay, I'm supposed to continue execution on line 4. Make a note of that. And then the second thing you have to do is to indicate that this column is no longer in use. So I use a strike through to indicate this column is no longer in use. And on line 4, what are we going to do? Oh, same thing. We are going from one n-defined sub to another n-defined sub. It's perfectly okay. There's no problem with this, because we just have to do the same thing again. What is my rightmost active return line number? It's not column D anymore. Column D is now deallocated, so column C becomes my only active return line number, let alone being the rightmost. So we have to use the return line number on that column to say that, okay, this reminds me to continue execution on line 10. Once I make that note, I have no use of this column anymore at this point, so I'm just going to deallocate that column and basically say column C is now available again. Are we doing okay so far with these concepts? Okay, allocate, deallocate, using the leftmost for allocation, using the rightmost to look up where we're supposed to go back to. Now we are continue execution on line 10. On line 10, it is invoking DEF. Guess what? Same boring stuff. Allocate the leftmost available column. But which column is my leftmost available?
C.
Column C, because it is now available again. So we are reallocating column C and say, okay, we're going to use it to remember where we are supposed to go back to when the subroutine is done. Where am I supposed to go back to?
Post.
Post, that's right, because there's no line after line 10, so that means when the subroutine is done, we are all done. And then the second thing an invoke statement is supposed to do is to continue execution in the subroutine. In this case, it's invoking DEF, and the first line and the only line inside that that actually does something useful is line 6 is adding 1 to X. X goes from 11 to 12, and then we move on to line 7. Line 7 is n-defined sub. It has got 2 things to do. Look up the rightmost active return line number. In this case, it is column C. It's the only return line number at this point. It's telling me to continue execution at post. All right, that's fine. We'll make a note of that. And then after that, we have no use of that column anymore, and then we'll deallocate it. And at that point, we can continue execution at post. Okay, that means we're all done. Okay, so what you were talking about, calling a subroutine from inside itself is like this. Okay, we still have 5 minutes left, so we can actually get into recursion. Recursion is kind of like this, but with recursion, I need to have conditional state. So we have defined sub, let's just call that, ABC again. So in this case, I can have something that looks like this. I can say, x gets x minus 1, and then with a conditional statement, I can say if x is still greater than 0, then invoke ABC from here. Okay. Now I need to do some indentations to make sure that everything looks right.
Until x is less than 0, specifically -1, unless x was less than 0 or 0.
Well, let's start with the value of, let's say, 2. Okay. Yep. So go ahead.
Plenty. That would be here for would say 2.
And then we'll invoke ABC, and we'll find out what's going to happen here. Now this concept is called recursion, and we will talk about recursion quite a bit in this class. Recursion looks kind of funny because you are invoking a subroutine from inside the subroutine itself. But to do this right is very boring. Okay, so I'm going to show you guys exactly why I call this boring. Okay,
Rather repetitive.
it is repetitive, and we are not doing anything differently. Okay, even though this looks like, hey, this is kind of interesting, and we have never talked about this before, we have actually talked about it already several times in this class. Okay, so we start execution on which line again? Which line is the first out of the definition of a subroutine? Line 7. On line 7, x gets initialized to 2. On line 8, we invoke a subroutine. Same boring 2 steps. Allocate the leftmost available column, label it return line number, and remember where we're supposed to go back to. In this case, we're supposed to go back to post because line 8 is the last line of the entire program. And then we continue execution in the subroutine. In this case, it's line 2. Okay, great. On line 2, we subtract 1 from x. X goes from 2 to 1. On line 3, we evaluate the condition. X is greater than 0 is true. So we have to move on to line 4. Line 4 says invoke ABC. Now, you don't have to, the only problem, the most important thing is don't overthink it. A lot of people overthink this and go like, how can I go from a subroutine to itself? You know, it doesn't make any sense. I'm not done defining the subroutine yet. Don't think that way, okay? Just think about the basic mechanisms of invoking a subroutine. Invoking ABC, invoking XYZ, invoking DEF doesn't make any difference, okay? It's the same mechanism. What is the mechanism? Allocate the leftmost available column. Remember where you're supposed to go back to. Now, this one is a little bit tricky because after line 4, we don't go to line 5, we go straight to line 6. So the return line number here has to be line 6. Because it's logically what is the next line that we are going to execute, not necessarily the line that is following it. So in this case, it's line 6. Okay? And the second thing invoke is going to do is to continue execution from the beginning of the subroutine that you're invoking. So which line am I supposed to go here? Go back to line 2. Exactly. So we continue execution on line 2, which subtracts 1 from x. X goes from 1 to 0. And then we go to line 3 again. X is 0. 0 is greater than 0 is false. So this time we're not going to go to line 4 to do the invoke again. And then we go to line 6. And line 6 says, we have to go to the rightmost active return line number to find out where we're supposed to go. Which column are we talking about?
E.
Column E is the rightmost. Okay. So column E says, continue execution on line 6. And guess what? That's exactly what we're going to do. It looks confusing because I'm going to make a note that we are going to continue execution on line 6. And then after that, this line 6 is going to deallocate the return line number column. So I'm going to format it and use a strike through to indicate this column is now deallocated. So now at this point, this line 6 is done. I'm continue execution on line 6 because this return line number told me to continue to execution on line 6. When I execute this line 6 on row 13, I will do exactly the same thing. Look up the rightmost return line number, which is column D in this case. It tells me to continue execution at post. Okay, we'll put post here. And then we have no use of column D anymore, which means I'm going to mark that column also as deallocated at this point. Now that this line 6 is all done, I continue execution at post, and I'm all done. That is recursion. Okay, so the key of understanding recursion is not to overthink it. Just think about what invoke is supposed to do and what end-defined stuff is supposed to do. The context is not important in this case. Yep, go ahead.
For when it goes return line number 6 in the E column, if you were to put 5, would you lose points for that?
It would be ambiguous because if you put 5, what are you going to do on line 5? It's the end if, right? Well, end if is not ambiguous, but if this is a while loop, like if you have an invoke right before end while, that would make it ambiguous because what does end while mean? Does it mean that you're getting out of the loop, or does it mean that you have to go back to the beginning of the loop? So that's why we want to kind of think about logically what is the next line to execute, and then use that as the return line number, and not just the line following the invoke statement. Right, exactly. That's a good question. So are we doing okay so far? All of this stuff is also in my notes, so if you read my notes, you will actually get to see all this stuff as well. It's just that in class I can do a presentation and explain things, kind of in an interleaved way.
Interactive way of reading your notes.
Exactly, because you can ask questions too. When you read a book, it's kind of hard to ask questions and expect an answer. You can ask questions all you want, but you may not get an answer. Yep,
When
no
you
road
get an answer,
today.
that's
So
when you guys start working.
free task for one day.